So for 10.8, we'll start out just with a reminder about the moments of inertia you need to have memorized. It's all of them except for the plates. So the thin rod through the center, through the edge, a disc, cylinder or ring, thin-walled sphere or a solid sphere. Those are the ones you need to have memorized. Now this section we introduce torque. Torque is the rotational equivalent of force. Really simple. And all we're doing is looking at how to calculate torque. And so the way you calculate torque is simply tau equals RF sine theta, or it equals R cross F. If we're talking about vectors, then we can talk about the cross product, and tau is a vector, and R is a vector, F is a vector, so R cross F, or RF sine theta, is how we calculate the torque. And the order matters. You stick your hands first in the direction of R, and then you curl your fingers in the direction of F. Right? So don't try to do F first and then R. You get the directions all mixed up. And so we have to use the right-hand rule for that. And so torque is, again, it's the analog of force, and it's what causes objects to have rotational acceleration, right? To change their angular velocity. You know, for example, turning a bolt with a wrench, and there are a few ways to vary the torque. One is to change the force, but also to change the angle of the pull. You know, go from 60 degrees to 90 degrees, make sure you're pulling perpendicular, you can increase torque that way, or you can increase the lever arm. You know, if you're trying to change a tire and you can't change it, sometimes people will take a big pipe and they put a pipe on the end of the wrench to make it longer, and then they can increase their torque that way. And so that's really it. RF sine theta, or R cross F, and then from there we have to use, we'll look at a few examples. Okay, so let's take a look at example 1. Here, this is the radius, and this is the force. So this is 2 meters, and the force is 5 newtons. And the way, again, we find this is by doing the right-hand rule, and it's R cross F. And again, the order is important. You go R first and then F. And so this turns out to be 10 newtons. And then how do we specify the direction of rotation? You could say it's either you know, the positive direction, you got your thumb pointing out, so it looks like this, or you could say counterclockwise. These are all ways of specifying the direction of the torque here. Right, the next one looks like this. This is 2 meter lever arm and the 5 Newton force on it. So again, it's 10 newtons, but this time it's in the negative direction. So you could say negative 10 newtons. This actually would be sufficient as the vector, the rotation vector, as your answer. Or you could do this, or say CW for clockwise. Example 3, it looks like this. This is the 2 meter lever arm, and this is the 5 Newton force. So again, R cross F, and so you've got, it's coming out this way in the positive direction. So you could say it's positive 10 newtons. Or you could do that, or counterclockwise, they all mean the same thing. Example 4, good if I number these. Here the angle between them is 0. So, I mean, think about this for a second. 2 newtons and 2 meters, and 5 newtons. If I have some lever arm coming out this way, and I'm pushing on it that way, directly into the pivot, then I don't get any torque. There's no torque there. So this is 0 Newton meters. Sorry, these should all be Newton meters. Sorry about that. And then this one, the last one, also same kind of thing. If the lever arm looks like this, you know, and I'm somehow like pulling on it this way with 5 newtons of force, I'm not getting any torque on this. So obviously we can see that the direction of the force matters. And so example 6 shows us two methods of figuring out the angles. Here, these are easy because they're 90 degrees. These are easy because they're 0 degrees. But now let's take a look at example 6 and how to break these things into components and find the angle that we need. So example 6, you've got the diagram there, and you've got, so it looks like this. Here's the lever arm, and then here's the direction of the force, and this is an angle of 60 degrees. Two ways of thinking about this. You can think of it either as going perpendicular to the line of action. So here's the line of action. The force is pulling in this direction. So you can extend that and then draw a line that's perpendicular. So it's kind of like taking the component of the arm that's perpendicular to the force. That's one way of thinking about it. The other way of thinking about it, and I like this one a little better, but it depends on the context, really. So if it's like this, here's this is 60 degrees. You can think of it as taking the component of the force that's perpendicular to the lever arm. This one makes a little bit more sense in my head personally, and that would be this, right? And this would then be like F sine of 60. So you can see it's a cross product relationship. We use sine of the angle. And so here in this case, if this is, do we actually have a number? So we don't actually have a number for this, but it would be R F sine of theta. And sine of theta also gives you this, right? If this is the lever arm, we're looking at the component of the lever arm that's perpendicular to this. So this is 60 degrees. We're looking at this component of the lever arm that's perpendicular to the force. So that's also sine of 60 degrees. So one way or another, it's RF sine of theta, where theta is the angle between the lever arm and the line of action of the force. Example 7, now we're looking at net torque. I think in terms of Newton's law, the net force, so we're going to look at the net torque on this. And you can see in the diagram, here's the point. This is 0.4 meters. There is a 5 Newton force pushing that way. And then half a meter away, there's another 5 Newton force pushing down. And so when I add these up, this is R cross F. So the net torque is torque 1 plus torque 2. Torque 1 we can say is this one, and this is going to be 5 times 0.5 meters, and then sine of whatever that angle is. I think the angle is 60 degrees. It is. This is 60. Again, we can think of this as taking the component of the force that's perpendicular to the lever arm. That's like this. This is 5 sine of 60 newtons. And so this first torque is to get the direction R cross F. It's pointing out. So this is positive, right, positive torque. We'd say 5 newtons times 0.5 meters times sine of 60. And then minus, I'm saying minus because this is R cross F, and I'm seeing this is clockwise, which is the negative direction. And so just like with linear vectors, with these I have to include the negatives to see how it all works out. And so this is going to be 5 newtons times 0.4 meters. Okay, and then you do that calculation, and you end up with 0.16 Newton meters. Okay, and it's positive, so you could write positive in front like that. You could say it is counterclockwise or that. Again, you don't have to do all of these, but I'm just saying any of these can work as specifying the direction of the rotation. Okay. Example 8. So here we have another kind of similar thing where we've got this the pivot in the middle and 1.5 meters. There's a force down of 480 newtons. And then here there is a downward force, I'll make it less, of 250 newtons. And this is 3 meters across. And now the question is, what is the net torque for the situation? So again, the net torque is going to be this torque plus this torque. Okay, this one's going this way, so R cross F coming out. So this is 250 times 3. This one's going to be negative, right? R cross F, so this is pointing into the board, so this is a negative torque. And this is 1.5 times 480. And I don't include any angles, it's sine of 90. Both of these, the line of action of the force is perpendicular to the arm, the lever arm. And so they're both sine of 91. And so I do this calculation, and we get 30, positive 30 Newton meters. That's part A. Part B looks like this. We want the net torque to be 0. We want it to be balanced. And so I want this to equal this. We're asking how far should this person sit in order for the seesaw to be balanced. And so this is staying the same. I'm saying I want 250 times 3 to equal 480 times what distance? And so when you solve for x in this, that's a 3, believe it or not, you get 1.56 meters. So if this person moved back a little bit, increasing the torque a little bit, then that would create a net torque of 0. Example 9, compound cylinder. So this is like we've got two cylinders put together, like a larger disc and a smaller disc, and they're together. It says find the net torque on the cylinder. Each force is provided by wrapping a massless string about the cylinder. Here's one of the key things. Anytime you see a problem like this, if I were to wrap a string around and pull, like this one, this angle is always 90 degrees. Strings always pull 90 degrees to the radius, because what it's going to do, it creates a tangent to the circle, no matter where you pull from. Okay, so keep that in mind. I've got that one, and I've got this one. This is 5 newtons. This one is also 5 newtons. And radii are 1 and 6. And so the net torque is simply, this one is positive, this one's negative. So 5 times 0.6 minus 5 times 1, and I end up with negative 0.4 Newton meters. That's the net torque about the axis. This next one, we have a non-uniform 5 kilogram cylinder. So again, same kind of thing. It's like I've got two discs put together, one larger, one smaller. There's a rope that's wrapped clockwise around the outer radius and counterclockwise on the inner radius. So then I'm going to have something like this. This outer radius pulling this way. This is a 5 Newton force, I'm told. This one on the inside is a 6 Newton force. This radius is 2.5 meters, and this radius is 0.5 meters. Okay, so this one, so I'm asking the net torque, right? So sigma tau, now we're really getting Greek, it's not even tau net, sigma tau, all Greek letters there. So negative 5 times 0.5. Again, sine of 90. We're wrapping a string around so it's perpendicular to the radius. And then plus this inner one goes this way, r cross f, and so it comes out 6 newtons times 2.5 meters. And I'm left with -1 Newton meters. All right, that's part A. Part B asks, what is the moment of inertia about the same axis? Okay, well, my moment of inertia for a disk is 1/2 mr squared. And so I is going to be 1/2 the mass of one of these times the radius squared. So let's say this is big M. So this is the big disk. Somebody was knocking. And so I'm going to call this big R squared plus 1/2, and then the mass of this one is going to be 5 minus M, because the whole thing is 5 kilograms. And so that means 5 minus whatever the big one is, so 5 minus M, and I'm going to do little r squared. I need to figure out somehow the ratio of these masses. Since they're both, since it's uniform, then I know that the mass is proportional to the area of the thing, right? So, sigma was the surface mass density, is m over a. So that's big M over A1, let's say, is equal to little m over A2. Okay. And I also know that m plus m is 5 kilograms. All right. So here, big M over pi times 0.5 squared, that's the big one, is little m over pi times 0.25 squared. So the pi's cancel out. I can replace this with big M minus 5. And so one way or another, and then you simplify these things, and what you're going to get is that big M is 4, and little m is 1 kilogram. So you take these, put them back in here. Now this is 4, this is 1. We know the radii. Right, and the whole thing ends up being 17 over 32 kilograms meters squared.
Have your attention, please. Reminder, please.
Thank you, Mr. Kushel. Okay, and the last example, 11, looks like this. It's really, really easy to overcomplicate this problem. It's actually really simple. Okay, it's like now we have a solid object. Instead of just a lever arm, like a single rod or something, now I've got a solid object. But I still use the same principle. So here's this thing. This is like, massless, a massless plate or something like that. Well, actually, it ends up working out to be 0, right? Where is the location of the torque from the square itself? It's not there. It's balanced. And so the only torque that's going to be added is the weight of this block of Play-Doh. And so what I'm going to do is I'm going to take the component of the lever arm. Right, here's the lever arm. But the component of the lever arm that's perpendicular to the force, here's the force, it's just the weight of the thing, is this. And this is 10 centimeters. I know that based on the information, it's 20 centimeters on the side. And so here's R, and here's F. So R cross F, I've taken the perpendicular component of R. So the torque is going to be 0.1 meters times the force, which is 2 newtons. Right, mg, I use 10 for g. And I get 0.2 newton meters. It's like this. So this is actually negative 0.2 newton meters say clockwise or draw the X with the circle around.